to be talking about conditional probability. All right, so previously we've covered a little bit about the probabilities of or, right? When you have A or B, and we've talked about probability of A and B, but now we're going to talk about conditional probability. This is like a slightly different animal. It's related, but it's also just different. And then we're going to define conditional probability. And in order to find conditional probability, we're going to talk a little bit about the multiplication rule. And this is going to be the mathematical way that conditional probability fits with these other probability spaces. Then we're going to talk about two common uses of conditional probability in statistics. A frequent one, and one that's commonly misunderstood, is in medical testing, which is sort of bad that it's commonly misunderstood too. And then we're also going to talk a little bit, just broadly, about how conditional probability is important in statistical inference. Okay, first let's talk about the difference between or, and conditional probability. And also, hopefully, you'll see the similarities as well. So previously, we used to draw these in terms of circles, but now I'm going to draw them in rectangles just to save some space here. So the probability of A or B, A and B being disjoint events, that might look like this, where we have A, here's the probability space for A, here's the probability space for B. And notice that there's no overlap. And when we talk about probability of A or B, what we're really talking about is what's the probability that you'll land in at least one of these shaded spaces. Same thing, very similar idea with probability of A or B with non-disjoint events. The only difference here is that now there are places where A and B slightly overlap, right? But once again, when you ask about the probability of A or B, you're really asking about what is the probability that you'll land somewhere in that shaded space. But when we talk about the probability of A and B, now, we really only want to know what is the probability of landing in that shaded space, just the part that overlaps, where both A is true and B is true. Remember, or is when at least one is true. This is when both have to be true. Okay, so this is all stuff we know so far. But now let's talk about the probability of B given A. So when there's this line, vertical line here, you want to read that as given A. So A, you already know is true. So here's the difference now. Now, you're thinking about this red space of A, right? That's A. This is the entire world now. And now we do not care about this part of space, this extra part. We don't care. Now A is our entire space, right? What is the probability that given A, we have B being true, right? So B. Now, there might be a portion of B out here as well, but we just don't care about it anymore because we only want to know the probability of B given A. So now that's the entire space I'm interested in. And this is the total space. All right? And so now let's draw out probability of A given B. Well, now your B is your entire space. That's the entire space that I'm interested in. And there might be some A out here, right? Let's draw like that. Let's draw like that. So there might be some A out there, but we just don't care about it. We don't care about any of this external space right here. Our whole world is now B. And all we care about is the probability of A given B. So you might want to think about within the world of B, within the given world, what's the probability of A, right? All right, so that's conditional probability. And the reason why it's called conditional probability is that first you have to meet a particular condition. You're shrinking down the space first. So here, we're now only in the condition where A is already true. We already know A. Only in that condition do we want to know when B is true. Same thing here. This is the condition now. Under the condition that B is true, what is the probability that A is true? And that's why it's called conditional probability. And so here, these are different because now we're not dealing with this entire space out here. We're only dealing with this world where some condition has already been met. Okay, so now let's get down into the nitty-gritty a little bit. Let's talk about and versus conditional probability, but let's talk about it in terms of actual numbers. So let's say I give you the situation where 2,000 computer science majors at a college were polled, and males were polled and females were polled, and they were asked, what kind of computer do you have? Do you have a desktop or a laptop? Now, it turns out that there are generally more males than females, and there are generally more people that own laptops than own desktops, right? But it also breaks down into little subcategories. Well, let's talk about OR first. Let me write this in blue, OR. Let's talk about OR. What is the probability that these students fall in the category of male or owns a laptop, right? And so here we think of that picture. You want to think of, okay, here's my males, right? There's all these males. And here are my laptop people, all these people who own laptops, right? But some of these laptop people are female, and some of these males own desktops, but that's okay. What we want to know is what is the probability that you'll land in any one of these spaces over the entire student body that was sampled. So that's the entire student body that's sampled, right? So really, you're looking for the probability of male or laptop over all students, right? But you also want to take out one of those overlaps or else you'll count this twice, right? So the probability that they're a male, right, is you want to look in the male column, right? You don't just want to look here. You want to look at the total number of males. That's 1,500 over 2,000, right? Because what I'm looking for is the probability of male plus, because I'm just using my generalized addition rule, and because these are non-disjoint events, we also need to subtract the probability of male and laptop. Actually, then, since we need that, let's start over here, because we need probability of male and laptop. So here, what is the probability that they are both male and they own a laptop? Well, we'd want to look in the male and owns a laptop. So that's 1,200 out of the entire student body. So it's just this overlap out of the entire box, entire space, right? And so that's 3 over 5. Okay, so that's 60%. So 60% of students are both male and own laptops, right? Now that we know that, it might be easier to do this. Then we want to add in the percentage of people who own laptops in general. So here we want to look across rows, and we see here there's 1,600 that own laptops, right, over 2,000. But notice that here, if you add these together, you're going to have a number that's over 2,000, right? And you can't possibly have this little colored-in space be more than the entire box, right? So what we need to do is take out the overlap. And the overlap are these 1,200 people. So if we look at this, what I'm just going to do is take 1,200 out of one of these guys. So that's 400. Add that here. So that's 1,900 over 2,000, right? And so if I want to turn that into a percentage, that's roughly 19 over 20. So that's 9.5 over 10, right? So that's 95%. Right? And so here we see that 95% of the students are either male or have laptops. It's a lot, right? So here we see the difference between the or statements as well as the and statements. But now that we know that, and those are just things we already know so far. Now that we know that, now let's start talking about conditional probability. So in conditional probability, we want to know, okay, people who already meet this requirement of having a laptop, under those conditions only. So now our world is limited to this. So now we don't pretend we put X's over everything else, right? Pretend we put X's. We only care about this world, people who own laptops. What is the probability of being a male given that they own a laptop, right? So instead of using this 2,000, now I'm going to use my 1,600 because that's my entire space now. And that probability is 1,200 over 1,600. And that's 6 over 8 or 3/4, and that's 75%. So 75% of, so the probability of male given laptop is 75%. Now let's look at a different condition where now we're looking at the probability that they are that they have a laptop given the condition that they are already males. So we already know we're limiting our world to here, and pretend we put X's over everything else, right? Now we want to know, given this little universe, what is the probability that they own a laptop? So that would be this number right here, that they're male and own a laptop, over this new world, right? It's not 2,000 anymore. It's just the people who are already males. And that's 12 over 15, which is 4 over 5, and that's 80%. Right? So notice that you might think that the probability of being a male given laptop is the same as the probability of laptop given male. But these are actually two different numbers. Why is that? Well, let's think about this. Here's my little world of male and laptop. In this case, my whole universe is this red universe. And I want to know, what is the probability of male given this universe, given the laptop universe? However, in this case, what I want to know, let me set up my world again. In this case, I have a new universe that I'm working with. I'm working with the universe of, given that they're a male, what's the probability that they own a laptop? So although this shaded in number is the same, right? This 1,200 is the same as this 1,200. It's this box right here, right? Even though that's the same, the world, the relative world that I'm looking at it in is different. Here there's 1,600 males. Here there's 1,600 people who own laptops. Here there's 1,500 males, right? And because of that, that changes our proportions, right? If you change the total, you change the proportion.